Next we'll talk about the independent samples t-test. So this is another inferential test that has a t-distribution for its sampling distribution. And you use this when you have two groups of participants and each person is in only one of those groups. And that's what it means by independent samples. They're independent in the sense is that the people in those different groups aren't connected with each other in any way. They're independent of one another. So you could have a caffeine condition and a decaffeinated condition, and you have different people in those two different groups. So the people in those groups would be independent of one another. It's also the case that you only use this when you have a scale-dependent variable, so your outcome variable has to be interval or ratio scale a measure. You also, when you're using these, you don't know the population means or the population standard deviation, and you'll be comparing two groups in this case. So really you're making inferences about two population means. The research hypothesis I'll use as an example for the independent samples t-test is that men do better on statistics exams than women do. Right, so you might think this is the case because you think men are better at math or something like that. The null hypothesis for this research hypothesis would be h sub naught, h sub 0, colon, the population mean for men is the same as the population mean for women. Right? So if the null hypothesis is true, the research hypothesis is wrong. If the null hypothesis is true, there's no difference. Nothing interesting is happening in the population. So next we'll go through the steps for doing an independent samples t-test. So the first step is going to be to just write out what your null hypothesis is. And here we're working with the research hypothesis that men do better on stats exams than women do. So the null hypothesis is going to say that they do exactly the same as each other. So h sub naught colon, the population mean for men, the average men's statistics score is exactly the same as women's average statistics exam score. The next thing we'll do is draw the population distributions. Notice there's two population distributions now. There's one for men and one for women. Right, and these are going to be frequency distributions over here like they have been in the past. This will end up being one for men and one for women. And this is the population distribution. These are individuals up here, individual men and women, the population level. Remember, this is if the null hypothesis is true. So this is the null hypothesis population distribution of individuals. There's actually two distributions up here now. They're both normally distributed. One is men, and the other one is women. And I'm trying to draw these so they're perfectly overlapping. So for this, if we say black is men, right, the null hypothesis says that these two distributions have the exact same mean. And there's more than one way to do these tests, but the ones we're going to do the one we're going to do in this class is going to assume that the standard deviation for women is the same as the population standard deviation for men. And notice we don't know what these population means are. We just know that they're the same as each other. And we don't know what the standard deviations of these distributions are, but we are ultimately going to have two estimates, one from each of our samples, of what this exact same shared number is. our third step will be to draw our observed samples. Now we have 2 observed samples. We have, and these are individuals, students' test scores. Remember, if we were doing research, this is all you'd actually ever observe. These are the data points you have. And SPSS does all this stuff behind the scenes. This is all under the hood, if you will. And these don't depend on the null hypothesis at all, like these do. These are what you expect if the null hypothesis is true. This is what you actually observe. So we're hoping to find observations inconsistent with the null hypothesis. So down here we have our exam scores. We'll say that this is men, and their distribution looks something like this. And we'll say women are over here. We'll say their distribution looks something like that. And we calculate the descriptive statistics for our 2 different samples. And we get the mean for men is 100. The standard deviation for men is 10. The sample size for men, and the number of men whose exam scores we have, is 100. And for women, we have a sample mean of 110. Women's standard deviation is 10, and the sample size for women is 100. And notice I'm keeping our 2 sample sizes the same, and that actually simplifies the math up here a bit. And so if you're working with a scenario for yourself where you have unequal sample sizes, then you won't be able to use some of the formulas that we use here. But just to keep things simple and easier to understand, we're going to go with equal sample sizes for now. All right, now that we have our observed sample distributions, we can actually figure out what our best guess is at the population standard deviation, because we have 2 estimates that we can use for our population standard deviation. And what we're going to do is we're going to combine those estimates. We're going to pool them. And with equal sample sizes, so I'm going to say this is approximately equal to the standard deviation across those 2 samples pooled. And to pool these 2, the formula is to take the standard deviation for men and square it, add that to the standard deviation for women squared, so the variances, add them together, and then divide by 2. That would give us the average variance, but we need a standard deviation, so we're going to take the square root of that to go from variances back to standard deviations. So this whole thing is under the square root here. So our S pooled for men is 10 squared is 100, plus for women it's 10 squared is 100, divided by 2 square root. 200 divided by 2 square root. 200 divided by 2 is 100 square root. So that's going to be 10. So 10 is our best guess at the population standard deviation for men and women. For these 2 distributions that are exactly the same, our best guess is the standard deviation of those distributions is 10, based on our observed samples. Next, what we'll do is figure out what the sampling distribution looks like for an independent samples t-test. And for this, let me spend just a little bit of time explaining what's going to be down here, right? So what we're trying to figure out with our independent samples t-test is if men and women have the exact same means as each other at the population level. And what we have for our observation is a sample mean for men and a sample mean for women. So what we can do is we can calculate the difference between those 2. The difference between those 2 sample means. And then we can see if the null hypothesis is true, how likely is it that you would get that kind of a difference between sample means due to random sampling if the null hypothesis is true. So what we're going to do, we want to compare apples to apples. So what we're going to do is create a sampling distribution that's a difference between sample means, but the kind that you would get due to random sampling if the null hypothesis is true. So for that, what we do is we take men's sample size of 100. So from the men's distribution, we randomly sample 100 of those men, calculate the calculate the sample mean for those 100 men. Take 100 women and calculate the mean of those 100 women. And then we're going to take that difference score, the male mean minus the female mean. I'll put a delta there. So this is the resulting difference score from subtracting the women's mean from the men's mean. And it's that difference score that's going to go down here. All right, so this is the sampling distribution if the null hypothesis is true, and this is a frequency distribution of these differences between sample means. And that's useful because what we can do is look at our observed difference between our sample means and see if that's the kind of difference that you expect due to random sampling when the null hypothesis is true. And we're hoping to find that the observed difference is so big, it's not the kind that you get from the null hypothesis being true. All right, so to create this whole distribution, we would do this for one pair of 100. We would do it for another sample of 100 men. Calculate that sample's mean, another sample of 100 women, calculate those women's mean, calculate that difference score. And we do that over and over for all these samples of 100, for every possible sample of male 100 test scores and women with 100 test scores and all the different scores between those, and that's what's down here. So that's going to be a t distribution. And then we need to figure out, well, what's its mean and what's its standard deviation. So the mean is actually pretty easy. It is going to be, of all of these difference scores, well, what's in the middle, right? What's the mean of those? And the most common difference score you're going to get is a difference of 0. Because if the men and women's means are the same up here, the most common difference across all the different samples you could get from that is 0. So this suggests that if men and women have the same population means, the most common kind of sample differences you'd expect would be 0, which makes sense. And then next we have to calculate the standard error, the standard deviation of this distribution. So it's going to be based on our sample mean, so I'll put an S here, and this is going to be the standard deviation or the standard error of men minus women. So this is the standard deviation of the differences between the means of men and women's samples. And to calculate this, it's got a little bit of a different formula than what we're familiar with here. What we're going to do is we're going to take, well, we can actually work right from the observed samples here. Let's do that. We'll take men's standard deviation, we're going to square it and divide it by the sample size for men. And this is hopefully familiar. It's a little bit different than what we usually do. Usually what we would have done to calculate a standard deviation down here is we take the population standard deviation and divide it by the square root of n, right? And ultimately we're going to take the square root of this. So if we wanted to make it a little more similar, we could just square this and then we get, so this is what's happening here. But for this difference, because it's the difference between means, we also want to include the women's. So what this is kind of the standard error of the men's distribution squared. This is the standard error of the women's sampling distribution squared, and we're adding them together. So that means that this is going to be like twice as wide as it was for one sample t-test. But these are variances, and we want a standard deviation, so we have to take the square root of our variances to get back to standard deviation units. All right. But basically what we have is the men's standard error that you get squared, the variance version, the women's standard error that you get squared. We're going to add those up, and then we're going to take the square root to get those variances back to standard deviations. And you might have wondered why, when we calculated this pooled standard deviation, we had to use variances rather than just standard deviations. And we're doing that again here where we're adding variances. And the reason is something called the variance sum law. So you don't add standard deviations together to average them, for example. You have to square them and turn them into variances first, which is what we're doing here and what we did when we created this pooled standard deviation to estimate our population standard deviation. All right, so we got our formula here for the standard deviation of the sampling distribution. So now we just got to plug our values in. So the standard deviation for men is 10, so we've got to square it to get 100. The sample size for men is 100. We're going to add to that women's standard deviation squared. So 10 squared is 100. This should be women's. So women's sample size, 100. And so we got all this filled in. The standard error. And so we got 1 plus 1 is 2. Square root of 2 is 1.414. So now we know that this standard deviation is male and women is 1.414. All right, so we've determined the characteristics of our sampling distribution in the sense that we got its mean and its standard deviation. It's a t-distribution as its shape, and remember, different t-distributions, there's different t-distributions for different degrees of freedom, and we'll come back to that in just a second. Next, we'll work on the critical region, or equivalently, the critical values. Right, and for this test, we'll use an alpha of 0.05, of course, like we always do. We'll do a two-tailed test. So given that information, now we go to our t table, and we determine our t critical values, right? So what these are going to do, these t critical values, are the t scores, the t statistics on this distribution, which are z-scores, where there's 2.5% of the area of that distribution beyond those z-scores. So it's two-tailed test, so we split this 0.05 on both sides. And so to look it up, we need to know our degrees of freedom. We'll call it the degrees of freedom total because we're actually going to get degrees of freedom from each of our groups. So degrees of freedom total of the degrees of freedom for men plus the degrees of freedom for women. And the degrees of freedom for men is just going to be the sample size of men minus 1. The degrees of freedom for women is going to be the sample size for women minus 1. So men's sample size 100, minus 1 is 99. Women's sample size is 100, minus 1 is 99. So degrees of freedom total is men's plus women's, 198. So you go to your t table, you try to find 198, and it's not going to be in there probably. And so what you're going to do is go to the next smallest degrees of freedom in your table, maybe 195 or 190, and whatever that smaller degrees of freedom's t critical value is, that's what we're going to use. So I did that earlier, and I found a t critical value of 1.98 for this case. Negative 1.98 over here, right? So our t critical, in this case, is plus or minus 1.98. Notice it's almost 1.96, which is the critical value when you have a perfectly normal distribution. That's the z critical when you do a z test, right? So we almost have a normal distribution here. And remember, the t distribution becomes more and more normally shaped the larger your sample sizes are. So we have pretty large sample sizes, so this turns into almost a normal distribution here. All right, our next step will be to calculate our test statistic. And remember, for all of our t-tests, our test statistic is a t-statistic. And the t-statistic is a z-score. And it's the z-score that tells us where our observed sample situation is on this distribution. And so in this case, the t-statistic is the difference between men's and women's observed means minus the mean of this distribution, which is 0, divided by the standard deviation of this distribution, which is, and notice whenever you're doing an independent samples t-test, you're always calculating your test statistic on this distribution, and for the independent samples t-test, this distribution always has a mean of 0. So if you want to, you can even simplify this by getting rid of that 0 because it never affects your t-statistic. And this is a simplified version of the formula, men's mean minus women's mean divided by the standard deviation of this distribution. So we'll plug in our values to calculate this t-statistic. Men was 100. Women was 110, so women did better on average. And the standard deviation, 1.414. So here we have negative 10 divided by 1.414, that's negative 7.07. So our t-statistic is negative 7.07. That means this observed difference between our means on this distribution was 7 standard deviations over this way. So this is about 2, 4, 6, 7. Our observed difference is way over here. So that's an extremely unlikely difference to come from these two populations if the null hypothesis is true due to random sampling. Next, we will decide to reject the null hypothesis, or not reject it, right? And so, as usual, what we'll do is we'll compare our test statistic with our critical value, and if our test statistic, our t-statistic, is more extreme, we reject the null hypothesis, and in this case, 7 is way more extreme than 2, so in this case we are going to reject the null hypothesis that men and women have the same test scores. All right, after we've decided to reject the null hypothesis, we need to interpret our findings. What did our study tell us? Well, if we would have failed to reject the null hypothesis, our study would be inconclusive. We would have wasted our time. But in this case, we rejected the null hypothesis. So we've decided out in the world the population mean for men and women is not the same. We rejected this possibility. This was super unlikely to be the case given these results that we had. So to interpret our findings here, what we do is we compare our observed mean for men and our observed mean for women. And what we find here is that women had a higher score on test exams than men. Well, that's not what we expected with our research hypothesis. We thought men would do better than women because we thought men were better at math. But it turns out with our data set here, we actually found the opposite of what we expected. Women did better than men at math. So in this case, to interpret our findings, we interpreted them such that women did better. This is at the population level. You could say the population mean for women, the average test score for women in statistics was greater than the average test score for men, right? And these are mu's, these are at the population level. So that's how we interpret these findings. We can go one step further in our interpretation, though, by calculating the effect size. Right, and the effect size, let me clean this up a little bit. The effect size, when you're comparing two different means, which we've done for all of our t-tests here and our z-test, is Cohen's d. Right, remember, that's up at this level. How many standard deviations away are the means, right? And here we're interested in the population mean for women and the population mean of men. Right, so here we're going to plug in our best guess at women's mean, which is the women women's and men's sample means. We put men's over here if we want. If we just switch them around, it would just make Cohen's d positive to negative or negative to positive. And this is how many standard deviations weigh at this level. So we want the population standard deviation. So in this case, what we'll do is we'll put in our best guess based on pooling the two observed samples. All right, so we can calculate our observed d here. So men was 100, women was 110. The pooled standard deviation was 10. So our Cohen's d is -1. So based on all the information we have from our samples, our best guess is that women, well, our best guess is that men's population mean is 1 standard deviation below women's. So that's a pretty substantial difference. Recall Cohen's d had the small, medium, and large reference points, small being plus or minus 0.2, medium being plus or minus 0.5, and large being plus or minus 0.8. So, right, a Cohen's d of 1 is actually a little bit larger than the reference point for large. So this scenario here has a large effect size, a very large effect size, you could even say if you wanted to. All right, so this is all the steps that you would go through. This is to do an independent samples t-test, right? And remember, this is all the observed data you have down here. So you just measure 100 men, 100 women, and you have this data. All of this stuff up here is what SPSS does behind the scenes. Whatever statistical program you're doing does all this stuff. So for you to understand what the computer program is doing, you have to be able to understand this stuff up here, which is why that's what we're focusing on in this class.